Welcome to this video on instruction formats. Understanding instruction formats is crucial in computer architecture and programming as they define how instructions are structured and interpreted by the CPU. Let us explore the various types of instruction formats and their significance. An instruction in a computer is composed of several groups known as fields, each containing specific information crucial for executing tasks. The most common fields found in an instruction are operand field, address field, mode field. Operand field, this field specifies the operation to be performed, such as addition, subtraction, multiplication, or any other arithmetic or logical function. It indicates to the CPU what action need to be taken with the provided operands. Address field, the address field contains the location of the operands that the operation will act upon. This can refer to specific memory address or a register with the CPU, allowing the processor to retrieve the necessary data for computation. Mode field. The mode field specifies how to find or access the operand. It defines the addressing mode, indicating whether the operand is a direct value, a memory location, or an indirect reference through pointers or registers. This field plays a vital role in determining how the CPU interprets the instruction and retrieves the recorded data. Three address instruction. Three address instructions allow for greater flexibility in operations by using three operands. In this format, the instructions specify two source operands and one destination operand. The result of the operand is stored in the destination operand. For example, add R1, R2, R3. In this instruction, the operation add specifies that the contents of the register R2 and R3 will be added together. The result of this addition will be stored in R1. Two address instructions. Two address instructions are more straightforward but less flexible. They use two operands where one of the operands serves as the both source and a destination. The result of the operation overrides one of the original operands. For example, add R1, R2. In this instruction, the operation add specifies that the contents of R2 will be added to the contents of R1. The result of this addition will replace the original value in R1. One address instruction. One address instruction uses a single operand with the operand type typically performed using an implied or specified register. In this format, the instructions specify one address or operand and the result is usually stored back in the same register. For example, add M. In this instruction, the operand odd specifies that the value stored at memory location M will be added to the value in the accumulator. The result of this addition is then stored back in the accumulator. Zero address instructions. Zero address instructions are primarily in stack-based architecture. In this format, no explicit operands are specified in the instruction itself. Instead, operations are performed on the top elements of the stack and the results are also pushed back onto the stack. Example, add. The operation add indicates that the two topmost values on the stack will be added together. The result is then back onto the top of the stack, effectively modifying the stack contents. Three address instruction utilize the three address fields to specify either registers or memory locations. This format allows for complex expression and operations to be performed in a single instruction, which can lead to shorter and more readable programs. The example, consider this expression, evaluate a plus b multiplied with c plus d. In this instruction, add r1, a, b. The first instruction adds a and b, store the result in the register r1. The second instruction add c and d, store the result in register r2. The final instruction multiplies the result r1 and r2, storing the final result in r3. This structured approach simplifies the expression evaluation process and keeps the program concise. Two address instructions are commonly used in commercial computers and allow for the specification of two addresses or operands in a single instruction. This format enables one of the operands to act as both a source and destination, facilitating efficient operations. The example provided demonstrate how to evaluate the expressions using two address instruction set. Here is a breakdown of each instruction in the assembly code. The first instruction move r1, a, move the value of a into register r1. Then next instruction add the value of b to r1, resulting in r1 is equal to a plus b. The next instruction move the value of c into register r2. Then add the value of d to r2, resulting r2 is equal to c plus d. Next instruction multiply r1 and r2, storing the result in r1. Then move the result of the multiplication into memory location x. This sequence efficiently evaluates the given arithmetic expression using basic operations in a two-address architecture. One address instruction utilizes an implied accumulator register for data manipulation. In this instruction format, one operand is stored in the accumulator while the other operand is specified as a register or memory location. This design simplifies the instruction set and makes it easier to perform operations. The example shows the expression using a one address instruction set. Here is the explanation of each instruction. Load A, load the value of A into the accumulator. Add B, add the value of B to the accumulator, resulting in AC is equal to A plus B. Store T, store the result from the accumulator into memory location T. And next, load C, load the value of C into accumulator. Then add D, add the value of D to the accumulator, resulting AC is equal to C plus D. Multiply T, multiply the value in the accumulator by the value stored in the memory location with the result stored in the accumulator. And finally, store X, store the result of the multiplication into memory location X. This sequence efficiently computes the expression using one address instruction set, utilizing an accumulator to perform arithmetic operations. Zero address instructions are primarily used in stack-based computers where operands are managed implicitly rather than specified directly in the instruction. In this format, no explicit address fields are provided. Instead, all objects are located and structured as a push-down stack. To evaluate the given expression using zero address instruction, the process may look like this. Push A, push A and to stack, push B and to stack, add, pop the top two elements A and B and add them and push the result back onto the stack, push C at the stack, push D at the stack, add, pop the two top elements C and D, add them and push the result back onto the stack, multiplication, pop the top two results A plus B and C plus D, multiply them and push the result back onto the stack. In this example, the values of A and B are pushed at the stack, followed by the addition operations, which results in A plus B being pushed back onto the stack. Similarly, C and D are pushed, added, and pushed back. Finally, these two results from the additions are multiplied, yielding the final result.